In this video we're going to look at the adder and subtractor. Now again, I have a full course on floating point addition and subtraction covering a 32-bit adder and subtractor. So if you're interested in all of the details, then I suggest you go and look at that course. What we have here is just one single video to give you an overview. Now I don't want to look at too much of the mathematics. I just want to try and keep this as practical and intuitive as possible. So we want to add and subtract numbers. Now if you go to the first part up here, we can see that we want to, for example, add a number x and a number y. Now let's say we want to subtract the number y from the number x. Well, and rather than creating a new process called subtraction, we can add on the negation of y. So in order to subtract y from x, we work out the negation of y and we go through the same addition algorithm. Now we could also have x minus y. Well, that's the same as saying x plus y. So again, we can negate the value of y and we can go through the addition algorithm. So we can see here that the subtraction algorithm can be generated from changing the inputs to an addition algorithm. So that's the first part of our simplification. Now there's a little bit more involved in it than what I've just shown here, but it gives you a good indication of what it is we're trying to do. Now if we look at the next little table here, what we have here is the sign of the number. So for example, is it a positive number or a negative number? So let's say we've got the sign of x and the sign of y. So we have the sign of x is positive and the sign of y is positive, and it could be negative positive, positive negative, and negative negative. Now I've put examples here of 4 examples here of actually doing this. So if we had, for example, a plus 7 and we added on a plus 5, we would get a plus 12. So you can see here the answer is going to give us a sign and it's going to give us an actual value. And we could do minus 7 plus 5, which would be minus 2, plus 7 minus 5, which is 2, and minus 7 minus 5, which is minus 12. So you can see here the first thing that we have to look at is the sign. So what is the sign of the result? Well, there's a neat little thing that we can do here. If we ensure that the value for our x is always greater than the value of our 5, now our y, now by greater I mean the absolute value, okay? So the absolute value here, 7, is greater than 5. The absolute value here, 7, is greater than 5, and again here and again here. So if we always ensure that this value here for x is always greater than y, then you'll notice that the sign of the answer is always given by the sign of the largest value. So for example, if we have a plus here and a plus, a minus, a minus, a plus, a plus, a minus, a minus. So we can get the sign of the answer by ensuring that we always subtract the smallest absolute value from the largest absolute value, and then we can take the sign as being the sign of the largest absolute value. So that's relatively straightforward here for working out the sign. Now there are other smaller complications, but we're not going to go into these. If you're interested, you can get it in the full course. Now the other thing we're interested in here is getting the actual answer. So you can see here the answer is either going to be a value of 12 or a value of 2. So in order to get the 12, we're going to add both together to get the 12. In order to get the 2, we're going to subtract. So we either go through an addition or we go through a subtraction. Now you can tell whether you're going through an addition or a subtraction by looking at the truth table. So this truth table here, for this little block, we're going to have the value here is positive, and positive will give you a positive. Now in the floating point land, we said that if the value is positive, we define it as a 0. If it's negative, we define it as a 1. So you could rewrite this little truth table and you could write it as, well, the positive is a value of 0, so we're going to have a 0 and we're going to have a 0, or we're going to have a 1 and a 0, or a 0 and a 1, or we're going to have a 1 and a 1. And you can see the outputs are given by these values here, which are going to be again a 0, a 1, a 1 and a 0. Now this little truth table is a truth table for an exclusive OR. So we can use the exclusive OR gate in order to tell whether we're going to go through an addition or a subtraction. So these are the two things that we need to know before we get started. We need to know the sign of the output and also whether it's an addition or a subtraction that will give us the correct result. So let's start off by looking at addition. Now I'm trying to keep the mathematics at a bare minimum and trying to explain this as intuitively as I can. There are two scenarios that we're interested in, and that is adding two numbers which are in the same range box and adding two numbers which aren't in the same range box. Now what do I mean by that? Now we understood that the exponent told us the range. So for example, if we had two numbers in the same range box, then that would be, for example, the range box 4 to 8, and we would be adding the number, say, 5 and the number 6, because those are in the same range box. If the numbers are in different range boxes, then we would be, for example, adding the number 5 and the number 12, and those numbers are in different exponent range boxes, and we have a slightly different algorithm depending on that case. Now I've worked through a little example here, but I've worked through the example rather than using the binary numbers. I've just worked through the example using decimal. It's easier to see what's happening, and it's maybe a little bit more intuitive for you. So let's say, for example, we're going to add the number 4.8 and 6.4. This gives us the number 11.2. But we can write this in exponent form as 1.2 times 2 to the power of 2, which gives us 4.8, and 1.6 times 2 to the power of 2, which gives us the number 6.4. But no, in this instance here, we have to keep this number here between the value of 1 and the value of 2. It can't be any greater than 2. So if the exponent is the same, 2 to the power 2 and 2 to the power 2, then we can simply add these numbers together. But in this instance, when we add these two numbers together, we get 2.8 times 2 to the power of 2. But as I said, this number here has got to be between 1 and 2, but it's now gone to 2.8. So in effect what we've got is a non-normalised number, and we have to normalise it. Okay, so we have to make this a number between 1 and 2. So we can do that by halving this number here. It becomes 1.4, and then we can double this number here. So we double this number by changing the 2 to a power of 3. So the little algorithm that we're interested in here is that for the mantissa, we're going to divide the mantissa by 2, and we're going to add 1 on to the exponent. So this is the little algorithm we have for adding two numbers together which are in the same exponent range. And this makes kind of sense. If you think about adding the mantissas together, then you're if we think about it in terms of our binary system, we're just adding two binary numbers together. Whenever we add two binary numbers together, whenever we get up to the most significant mantissa value, then there's a chance that that most significant mantissa value would be a 1 and a 1 for both numbers. So whenever we add those together, we would get a 0 and we would carry 1 over. So when we carry 1 over, in effect we're carrying 1 over into the exponent range. So the exponent goes up by 1. That is, we've gone up an exponent range. So that's the simple one for the same exponent. Now if we have a different exponent, we do it slightly differently. So let's look at that next. So here are two examples, again using the base 10, which will describe to us what happens whenever we are adding numbers together which are in different exponent ranges. So we've got the number 80,000 plus 4,000. We add those together, we get 84,000. So that can be written as 8 times 10 to the 4 plus 4 times 10 to the 3. But we can add these together. We can only add the numbers together if the exponent is the same value. So we're going to have to make this exponent number here the same as the exponent number here. So that is, we're going to have to change this 3 to a 4. So we've done this here, we've changed it 3 to a 4. But if we change this by a factor of 10, we're going to have to make this number a factor of 10 smaller. So instead of being 4, it's going to have to be 0.4. So we've got this number now plus this number, and you can see here that the exponents are the same. So if the exponents are the same, we can simply add these together. So we're going to have 8.4 times 10 to the power of 4. Now whenever we look at these, if we look at the difference in the exponent range, in this case here we're going to have e to the x minus ey. So the exponent range for x is 4 and the exponent range for y is 3. So the difference here is a difference of a value of 1. Now when we look at the mantissa, what's going to happen with the mantissa? In this case we've had to normalise. So that is, we've had to shift the mantissa. So you can see that the result is going to be the mantissa for x plus, well, it's the mantissa for y, but it's the mantissa for y which has been divided by this 10 to the power of e to the x minus e to the y. In this instance, it's just a value of 1 in this case, so it's just a factor of 10 that this has been reduced by. So in this case here, this is just a value of 1, 10 to the power of 1, my has been reduced by a factor of 10. Now whenever we look at this here, we're going to have the value of our mantissa is going to be greater than or equal to 1 and less than a value of 10. So it means that the result here can just be written as m result, which is whatever this number is, times 10 to the power of our exponent value for x. So that's a straightforward calculation. Now there's one other example here, and it's got 95,000 plus 7,000. It gives you this result here. So whenever we work through this one here, we get this number here and we get this number here. We cannot add them because the exponents are not the same. So what we do is we add one onto the exponent and we divide this by a value of 10. So we get this result here. But now when you look at this result here, this result isn't a normalised result because the decimal point is here. We need to move the decimal point to this point here. So it means we're going to have to shift the values here. So this becomes 1.02 times 10 to the 5, okay? So it means that the exponent changes from 4 to 5 and the mantissa changes as well. It goes down by a factor of 10. So the exponent can go up by 1, but the mantissa has to go down by 10. And that's what this little algorithm here tells us. The final result we get, the exponent increases by 1, but the mantissa decreases by 10. So there's different little algorithms that can occur depending on what numbers you have. So this is the little algorithm for the addition. A number x plus a number y, we're going to have mx plus my, but my could decrease by a factor of 2 to the difference in the exponent values, and we're going to have the value for the exponent, it will just remain at the value of the exponent for x. So we'll have the final result here, mrbex. Now both of these numbers, mx and my, have to be between 1 and 2. And we will have the two options. If the value for the mantissa ends up greater than 2, then we're going to have to normalise. That is, we're going to ripple the value of 1 through the mantissa up into the exponent. So therefore the mantissa will decrease by a factor of 2, but the exponent will go up by this value 1. So this is the output here for the mantissa. The other option is that we don't have this ripple effect. So there is no ripple and there is no addition on to the exponent value. So we won't go through all of the details of subtraction, but this gives us an indication of what is happening. So we can subtract y from x, and again we subtract off the values for the mantissa for y from the mantissa for x, and we get our final result. Now we have options here, so if the result of the mantissa is greater than or equal to 2, well, that can't actually occur. We've got the option the result is between 1 and 2, in which case we don't have any ripple occurring and we don't have any change in the mantissa. So this is the simplest case. Now, one complication we have with subtraction is when we subtract two numbers together which are very, very close, we can get a very tiny number, and this is something referred to as cancellation. So in this case here, we generate something called a leading zero count. So we count these leading zeros, and this is the number lambda, and this is the little equation that determines the output. So we're going to have 2 to the power of this leading zero count, and the value for our exponent is going to be the result, and we're going to subtract off this leading zero count. Now, I haven't gone through any details as to why that is the case. If you're really interested in all of the details, then if you go through and do the entire course on the 32-bit adder and subtractor, you'll be able to work out everything that is going on. But we don't need to know this level of detail in order for us to continue with design a CPU 4. So in the next video, we will look at the actual circuit in Logisim for our adder and subtractor. That's all for this video. Thank you for listening. I'll get you on the next video. Goodbye.